Welcome to our exciting journey into statistical mechanics. Today we are diving into a CSIR Net PYQ 2012 June exam, exploring the fascinating world of probability, thermodynamics, and molecular behavior. And get ready to unravel the secret of energy, entropy, and the equilibrium, and boost your knowledge for success in the CSIR Net exam. Okay, and it's very much needful for your exam purpose because the previous year questions matters in your exam hall. Okay, so let's start, and welcome to our channel Physics Cat. First question 39. Okay, and it is said that consider a system of non-interacting particles in d dimensions obeying the dispersion relation E equal to a k to the power s. Fine. Where E is the energy and k is the wave vector and s is just an integer, a constant, and the density of state n of E is proportional to you need to calculate. Good. So first of all, you need to write one thing, the dispersion relation. Dispersion relation, you know, E equal to a k to the power s. Good. And the volume of sphere in d dimension in k space, I mean volume of sphere in d dimension and in k space, okay, equal to pi d by 2 and d by 2 factorial k to the power d, where d is the dimension in k space, right? Okay, so the number of microstate, you can write number of microstate is proportional to k to the power d. Okay, and this is omega varies e to the power d by s. Good. Okay, this is the number of microstate, right? And the number of microstate in a range e to e plus d. Okay, this is needful, and this is proportional to I mean d omega is proportional to e to the power d by s minus 1 into d, right? Okay, and this is the density of state, and this is the answer. So this is proportional to epsilon d by s minus 1. This is your answer, right? Okay, now let's jump into the next question, and the number of ways in which n identical bosons. Okay, 1 minute. Okay, 40. The number of ways of which n identical bosons can be distributed in two. I have got one information that the particles are bosons. Okay, but if it is said that they are fermions, then the number of microstate, you know, omega equal to k particles or in classical nature, then sigma classical, sorry, omega classical equal to k to the power n. But these are bosons. Okay, so for bosons, the number of microstate, I think you have the basic concepts about this. Sigma equal to k plus n minus 1 factorial by k minus 1 factorial n factorial, right? Uh, Number of bosons can be distributed in two energy levels. So energy levels are given. So k equal to 2, this is given, this is not given. So k equal to 2 is given. If you substitute this value in this, then you will write n plus 2 minus 1 factorial by 2 minus 1 factorial n factorial. Okay, and then this is the simple math, n plus 1 n factorial by n factorial, and these two are cancelled out, so n plus 1. This is the answer. Okay, and let's go for the next question. Yes, n particle in a volume V and the temperature T is F equal to n kBT ln. Okay, I mean the free energy is given where A0 is constant. The internal energy of the gas you need to calculate. So first of all, I will write the formula. What's it's given? Okay, and it's given F equal to n kBT ln A0V kBT whole to the power 3 by 2 by n, right? And here A0 is constant and kB is the Boltzmann constant. Okay, so you need to calculate the internal energy, right? So you can write it kBT ln A0V kBT whole to the power 3 by n whole n. You can write it. Good. And also you know from the statistical mechanics lecture that F equal to minus kbt ln q, and this q is called by the partition function. Good. So you know this and you have got this. So if I write this is equation number 1 and this is equation number 2, and if I compare this both equation, then you will get ln q, sorry, one minute, ln q equal to minus ln a0v kVt whole to the power 5/2 by n, okay, and this is n, right? And also you know that so you have got the ln q, and now it's very easy for you to calculate the internal energy U, and because you know U equal to minus del beta ln q. Okay. But you can see that in this equation there are no term for beta. So how can you calculate this derivative with respect to the beta? Okay, so you need to transfer this beta by t because there are a function t. Okay, so you know beta equal to 1 by kbt, right? And from here del beta equal to minus 1 by kbt square del t, right? Okay, now substitute this, so you can write minus del beta ln q equal to kb t square del t ln q. Now it's okay and it's comfortable for calculating. Good. Okay. Now just simple derivative kbt square del t and put this value, so minus ln a0v kVt whole to the power 5/2 by n, and this is n. Okay, now I will make the calculation derivative part. Okay, so kVt square, and if I rearrange this, okay, then you may write del t minus ln t5 by 5/2 minus ln a0v kv by n whole to the power n. I can write this. Okay, just check the calculations. Okay, and then you can see that there are no t term, right? And here is only t term, so the derivative will go through only this t term. Okay, so kb t square. This is logarithm functions 5n by t, and ln t, the derivative of ln t equal to 1 by t. Good. So 5n by 2 kv t, right? 5/2 n kv t. This is answer. Okay. So this is an interesting question. Now let's go for another question. Question number 63. Consider black body radiation contained in a cavity whose walls are at temperature T and the radiation is in equilibrium with the walls with of the cavity. Okay, if the temperature of the walls is increased to 2T, and I mean the initial temperature is T and was T, and later 2T. Good. And radiation is allowed to come to equilibrium at a new temperature. The entropy of the radiation increased by the factor of. Okay. And in black body radiation, so 63, in black body radiation, entropy S is proportional to TQ. From here I can write S1 by S2 equal to T1 by T2, because S is directly proportional to T. I can write this T1 by T2, and the temperature is given. Okay, I need to calculate S2, so write this as S2 equal to 2T by T whole cube, because the final temperature is 2T and the initial temperature is T. So I substituted this, and T2 equal to 2T and T1 equal to T, and here S1 by S2. So if I want to get the value of S2, then S2 equal to, this will be the inverse, so 2T by T whole to the power Q, and you can, this T will be omitted, and 2 to the power Q, so 8 is the answer. So this is small, okay, but you need to remember this formula, otherwise this question can't be solved. This is actually 5 marks question in part 3 in CSIR NEET. Okay. And it's given a system has two normal modes of vibration with frequency omega1 and omega2 equal to 2 omega1. That's good. What's the probability at a temperature T the system has energy less than 4 each cut omega1. Okay, and in the following x equal to the minus bh beta h cut omega and z is the partition functions. Okay, so first of all, one minute. Two normal modes of vibration exists, and the frequencies are also different. So one is omega 1 and second one is omega 2. Okay, so I can write the possible energies of the system. Possible energies equal to n plus 1 by 2 h cut omega 1 plus n plus 1 by 2 h cut omega, where n m equal to 0, 1, 2, 3, dot, right? And sorry, this is omega 2. This is totally different frequency, right? And if you then substitute n plus 1 by 2 h cut omega 1 plus n plus 1 by 2 2 h cut omega 1, right? And the possible and if you now calculate the degeneracies, I mean the corresponding degeneracies, okay, then you need to find the possible ways to arrange the n and m, and the total number, total amount of energy should be less than 4 h cut omega 1. Okay, should be less than 4 h cut omega 1. Okay, choose the ways: n equal to 0, m equal to 0, n equal to 1, m equal to 0, n equal to 0, m equal to 1, and n equal to 2, m equal to 0. Okay, let's find the energies. So first, E1 equal to 1 by 2 h cut 1, because n equal to 0, plus 1 by 2 into 2 h cut omega 1, and this is E1 equal to 3 by 2 h cut omega 1, right? And this is G1 equal to 1. Okay, and E2 equal to 3 by 2 h cut omega 1 plus 1 by 2 into 2 h cut omega 1. So E2 equal to 5 by 2 h cut omega 1, right? And E3, for E3, this is n equal to 0, m equal to 1, right? So 1 by 2 h cut omega 1 plus 3 by 2 into 2 h cut omega 1, right? And E3 equal to 7 by 2 h cut omega 1. And same for here, E4 equal to 5 by 2 h cut omega 1 plus 1 by 2 into 2 h cut omega 1, and E4 equal to 7 by 2 h cut omega. Now you can see this two. You can see that both are same. So here degeneracy G equal to 2, and I can write this is E3. This is not the different energy level E3 and E4. I can write it as E3, and I will choose only one. Okay, so let's find the probability at a temperature T. Okay, and the system has energy less than 4 h cut omega 1, and so the probability P equal to P1 plus P2 plus P3, right? Where we know Pi equal to, I mean the probability that at temperature T, okay, Pi equal to Gi exponential minus beta Ei by Z, where Z is the partition function, right? And so write this e to the power minus 3 by h cut omega. Degeneracy is always 1 because there is only one state available by Z, plus e to the power minus 5 by 2 h cut omega by Z. Degeneracy 1 because only one state available. This is E2, right? Plus 2 into e to the power minus 7 by 2 h cut omega. This is 2 state available. So this is degeneracy G equal to 2, and this is Z. Okay, so 3 by 2 h cut omega 1 by Z into 1 plus e to the power minus beta h cut omega 1, okay, plus 2 e to the power minus 2 beta h cut omega 1. And in the question it is given that x equal to e to the power minus beta h cut omega 1, right? So I can replace it by writing x to the power 3 by 2 by Z, okay, into 1 plus x square, and this is the answer. Okay, this is a lengthy question, but easy question also if you know the process and the appropriate recipe to go forward. Okay, I'm going for the next question, and question this is 62, right? And said this is from Bose-Einstein condensation. Bose condensation occurs in liquid helium. Helium-4 kept at ambient pressure at 2.17 Kelvin, at which temperature will Bose condensation occur in helium-4 in gaseous state, the density of which is 1000 times smaller than that of the liquid He4. Assume that it's a perfect Bose gas. That, just a teeny formula you need to remember, and this calculation will be more easier to you. And let's see this. What's the formula? And I think you have already thinking about this formula, that for Bose-Einstein condensation, TB varies n to the power 2 by 3, and n equal to particle density. And I will suggest that try to keep all the teeny formulas from Bose-Einstein condensation, I mean the quantum statistics, try to remember in your mind for always, because the questions nature is very small and teeny, but if you don't know the formula, then this question will be destructive for yourself. From here you can write TB liquid by TB gas equal to N liquid by N gas. I can write it? I think I can write it. Now substitute this. A condition is given that the temperature will Bose condensation occur in helium-4 in gaseous state, the density of which is 100 times smaller than that of the liquid helium-4. So I can write it as N liquid by, this is the N gas, so N liquid by 1000. Okay, and this is 2 by 3, and you will get 1000 whole to the power 2 by 3, and this is 100, right? Now TB gas equal to TB, sorry for this, TB liquid by 100, and this is given, so 2.17 K by 1000 equal to 21.7 millikelvin. This is the answer. Okay, that's all for today's statistical physics practice session. I hope you found it helpful. Okay, don't forget to subscribe my YouTube channel Physics Cat for more practice questions and explanation to smooth out your learning journey. And good luck on your exams. Okay, and I will see you in the next video. On probably on the topic December 2012 previous year questions. Okay, so thank you.